Welcome to This Explainer. Today we're diving straight into Chapter 8, Application of Integrals. Have you ever looked at the world around you and wondered exactly how we measure all those complex, fluid, curvy shapes that make up nature and architecture? Well, you're definitely in the right place. We're going to unpack the elegant mathematical machinery that lets us do exactly that.
It all really starts with a seemingly simple question. How do you measure a curve? I mean, think about it. We're all incredibly comfortable with straight lines. Give just about anyone a ruler and they can easily find the area of a rectangle or a triangle. But here's the catch. Nature rarely deals in perfectly straight lines. So what happens when the lines get curvy? How do we actually calculate the space inside a sweeping parabola, or say an elliptical orbit? That is the exact puzzle we're solving today.
Here's our roadmap for today. First, we'll move beyond basic geometry. Second, the magic of slicing. Third, calculating circles and ellipses. Fourth, navigating the x-axis. And finally, meeting the pioneers of calculus.
Let's jump into Section 1, Beyond Basic Geometry. We're looking at the strict limits of everyday math.
Now, elementary geometry is fantastic. It gives us the fundamental formulas for triangles, rectangles, trapezoids, you name it. And these are absolutely crucial for countless real-life applications. But they're completely inadequate when we step into the realm of curves. To find the area enclosed by parabolas, ellipses, or really any arbitrary curve, we have to graduate from basic geometry and bring in the heavy machinery. We need integral calculus.
All right, moving on to Section 2, the magic of slicing. Let's talk about the elementary area.
The absolutely crucial concept here is the elementary area. Imagine you have this curvy region that you need to measure. Well, calculus tells us, hey, don't try to measure the whole thing at once. Instead, imagine slicing that region up into a huge number of incredibly thin vertical strips. If we look at just one arbitrary strip, it has a height of y and a tiny, almost infinitely small width that we call dx. The area of this single elementary strip is simply height times width, or y times dx. It basically acts just like an infinitely tiny rectangle.
To actually pull this off, it's a simple three-step process. First, define your boundary. You need to identify the function of your curve, which is y equals f of x. Next, choose your weapon. Are you going with vertical or horizontal strips? Finally, sweep across the shape by integrating between your boundary lines, from A to B. This brilliantly illustrates what a definite integral actually is. It's literally just the result of adding up all those tiny elementary areas, all those little y dx strips, sweeping right across the region from point A to point B.
But you might be wondering, what if your curve is oriented completely differently? Well, the slicing method works perfectly sideways too. Instead of vertical strips, we can just use horizontal strips. The logic is totally identical, but our area formula shifts just a bit. In this case, the width of the strip is a tiny segment on the y-axis, which we call dy, and the length is x. So we just integrate x times dy between our vertical bounds c and d. It gives us the exact same incredible measuring power, just from a different angle.
Section 3, Calculating Circles and Ellipses. Time to apply the magic.
Let's look at a circle with the classic equation x squared plus y squared equals a squared. The cool part? We don't even need to integrate the entire thing. Because a circle is perfectly symmetrical across both the x and y axes, we can just find the area of the region in the very first positive quadrant. We integrate from 0 to a using our vertical strips and then simply multiply that result by 4. It's such a remarkably efficient shortcut.
And when we actually run that integral, skipping over the complex trigonometry and substitution for just a moment, the final result drops out beautifully. The area enclosed by our circle is exactly pi times a squared. It perfectly matches the classical formula we all memorized back in elementary geometry. Except now we've actually proven it using the rigorous additive power of calculus.
Okay, but how about a shape that's a bit more stretched out? For an ellipse, the equation gets slightly more complex, sure, but that elegant slicing process, it applies in the exact same way. We isolate the y, set up our integral for just that first quadrant from 0 to a, and then multiply the whole thing by 4 using that same powerful principle of symmetry.
After doing the integration, we arrive at this pristine derived formula. The area of an ellipse is pi times a times b, where a and b represent the semi-major and semi-minor axis. Honestly, it's incredibly satisfying to see how integral calculus cleanly handles the stretched nature of the ellipse, giving us this beautifully simple, universal formula.
On to Section 4, Navigating the x-axis. Let's look at how we handle negative areas.
Now, a cosine wave between 0 and 2 pi is the perfect example of a pretty tricky scenario.
You see, this curve doesn't just stay neatly in positive territory, it dips down and crosses right below the x-axis. If we just went ahead and integrated this entire wave from start to finish in one go, the positive areas above the axis and the negative areas below the axis would mathematically cancel each other out. That would give us a total area of 0. And obviously looking at it, the physical area here is definitely not 0.
So to make sure we don't accidentally calculate an area of 0, we have to follow some fundamental rules. First, you've got to identify the specific portions of the curve that fall below the x-axis. You need to understand that the definite integral for those sections will yield a mathematically negative number. So to fix this, we simply take the absolute value of that negative area, turning it positive. Finally, we break the problem into separate chunks, summing the absolute value of the lower portions with the regular value of the upper portions. Seriously, skipping this step is exactly how you'd end up mathematically proving a physical object has 0 mass, which, as you can imagine, is a pretty dangerous mistake in engineering. Which brings us to Section 5, the pioneers of calculus. Time for some historical origins.
The timeline of these ideas is absolutely staggering. Believe it or not, the origin of integral calculus actually goes all the way back to ancient Greece, around 300 BC. Brilliant minds like Archimedes used something called the method of exhaustion to calculate the areas of plane figures. But the systematic approach to calculus, the one we know today, didn't really erupt until the 17th century, driven completely independently by Isaac Newton and Gottfried Wilhelm Leibniz. We're talking about a massive leap across centuries of mathematical evolution.
But the story certainly doesn't end in the 17th century. While Newton and Leibniz developed those fundamental concepts, it was actually A.L. Cauchy in the early 19th century who finally brought the crucial, rigorous concept of limits to the theory. It was Cauchy's work that provided the true mathematical justification for why adding up all those infinitely thin elementary areas actually, well, works.
Just consider this powerful quote from mathematician Lie Sophie. It perfectly highlights that while the core conceptions go way back to Archimedes and others, the true breakthrough, that realization that differentiation and integration are actually inverse operations, belongs to both Newton and Leibniz. Despite their incredibly famous rivalry and completely independent approaches, their combined discoveries literally changed how we understand and measure the natural world. So the next time you look at a sweeping architectural arch, or maybe just the curve of a falling object, ask yourself, exactly how many infinitely thin slices would it take for you to measure it?